Hey guys, Mr. Nazarevich here, and I'm going to be going over the free response questions for the midterm. So here's problem one, and you've got the lead up, you've got three targeted sites, river X, river Y, and river Z, and you've got measurements when you're looking at the concentration of aldrin. So the first question says, compare the distributions of the concentration of aldrin among the three different rivers. So when you're comparing distributions, we want to talk about SOCs. So let's talk about shape and outliers first. So there are no obvious outliers. Actually, I could just say there's no outliers for any of them. And no obvious skew. For all three sites. Now, the median concentration of, when we're talking about box plots, for measure of center, I'm going to talk about the median. As you can see, the median of river X is greater than the median of river Y, which is greater than the median for river Z. That's what we want to say about center. For spread, the range and interquartile range and IQR is greatest for river X and smallest for river Z. So we can say, so that compares the shape, no obvious skew. Outliers, there's no outliers for any of them. The center, the median is greater for X than Y than Z. And for spread, the range and interquartile range is greater for X than Y, and then Z is the smallest. So that's the SOCs for that. I'm going to erase this so that I have more room for the other question. All right, so next question. Construct a stem plot that displays the concentration of aldrin for river X. And it gives us the concentrations. All right, so stem plot. We're going to start with 3, 4, 5, 6, 7, 8. All right, so we have 3.4. 4.0, 5.6, 3.7, 8.0, 5.5, 5.3, 4.2 and 4.3, 7.3, 8.6, 5.1, 8.7, 4.6, 7.5. Looks like 5.3 is in there. 8.2, 4.7, 4.8, and 4.6. Describe a characteristic of the distribution of aldrin concentration in river X. Oh, key. That's the other thing. Whenever you're making a stem plot, you want to make sure that you include a key. So we'll say 3.4 represents a concentration like this, 3.4 of 3.4 parts per million. Describe a characteristic of the distribution of aldrin concentration over X that can be seen in the stem plot but cannot be seen in the box plot. The shape has two clusters and a gap between 5.6 and 7.3. So that can be seen from the stem plot. You've got the two clusters and a gap. All right, let's look at the next question. Researchers studying a pack of gray wolves in North America collected data on the length x in meters from the nose to tip of tail and the weight y in kilograms of the wolves. The scatter plot of weight versus length revealed a relationship between the two variables described as positive, linear, and strong. For the situation described above, explain what is meant by each of the following words. Positive. As weight increases, so does length. Linear. The data is best modeled by a line. Strong. The expected and actual I'll actually change that a little bit. I'll say the data doesn't deviate much from the line. So the data collected from the wolves were used to create a least squares regression line. Y hat is negative 16.46 plus 35.02x. Interpret the meaning of the slope of the least squares regression line in context. So the slope is the thing that's next to the x. And I'm going to put the here for the sake of space, how to interpret that in context. For each additional meter of length, and here's the key, we expect a wolf to weigh an additional 35.02 kilograms. One wolf in the pack with a length of 1.4 meters has a residual of negative 9.67 kilograms. What's the weight of the wolf? All right, so residual is actual minus predicted. And we know the wolf had a residual of negative 9.67. What's the weight of the wolf? The actual we don't know, minus the predicted. We're going to put the 1.4 in over here. So let's see. I'll just use one of these calculators. My license has expired on my other one, so I'm very sad. I'll try to get a new license soon. All right, but for the time being, we're going to do 35.02 times 1.4 is that, minus 16.46 gives me 32.57. So minus 32.57. So I'm now going to add that to, oops, So essentially what I'm doing is I'm subtracting 9.67 from that. I should get 22.57 22.9. So my actual is 22.9 kilograms. There it is. So residual is actual minus predicted. Okay, let's look at problem number 3. Windmills generate electricity by transferring energy from wind to turbine. A study was conducted to examine the relationship between wind velocity in miles per hour and the electricity production in amps for one particular windmill. For the windmill, measurements were taken on 25 randomly selected days, and the computer output for the regression analysis for predicted electricity production based on wind velocity is given below. The regression model assumptions were checked and determined to be reasonable over an interval, wind speeds represented in the data, which were from 10 miles per hour to 40 miles per hour. Use the computer output determined above to determine the equation of the least squares regression line. Identify all variables in the equation. All right, so constant, the thing that says constant, it's going to be my y-intercept. So I will have y hat is 0.137 plus 0.240x, and I'm going to identify all the variables. So y hat is, so I want to examine the relation between wind velocity in miles per hour and electrical output in amps. So that's the electrical output. Predicted electrical output. And x is my wind velocity. So I have the equation and identified all the variables used in the equation. How much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on the day when the wind velocity is 15 miles per hour? All right, so the way I would do this one is I would take 15 and 25, plug both of them into my equation. Let me actually try to do that here. I will try to do that here. So all right, let me look at what my equation is. So 0.137 plus 240, 137 and 240. So I want times 25, and I want the same thing. And then I want to subtract the 2. So 2.4, that is my, that's my difference. So the difference is 2.4, and what's the units? Electricity in amps. That's my units. What proportion of the variation in electricity production is explained by the linear relationship with wind velocity? All right, so when you start seeing a question like that, you want to think to yourself coefficient of determination. And the coefficient of determination is the r squared. So 87.3%. Is there statistically convincing evidence that electricity production by the windmill is related to wind velocity? Yes. The r squared value is quite high. So 87.3% of the electrical production can be explained by the variations in wind velocity. So that's a pretty high R squared value. All right, so that is problem 2 and problem 3. Let's go to problem 4. Alzheimer's disease results in loss of cognitive ability beyond what is expected with typical aging. A local newspaper published an article with the following headline. So I looked at the medical histories of 21,000 men and women for 23 years. The article stated that for those who smoked at least 2 packs of cigarettes a day, the risk of developing Alzheimer's disease was 2.57 times greater than the risk of those who did not smoke. Identify the explanatory and response variables in the study. So the explanatory variable is smoking or not smoking at least 2 packs per day. The response variable is developing Alzheimer's. Is the study described in the article an observational study or an experiment? Obs study, treatment, not imposed. Exercise status, regular weekly exercise versus no regular weekly exercise, was mentioned in the article as a possible confounding variable. Explain how exercise status could be a confounding variable in the study. So, people who exercise. So when you answer a question like that, you want to tie it to both the explanatory and response variable. So people who exercise might be more health conscious, and thus less likely to smoke. So in addition, also smoking or exercise might prevent onset of Alzheimer's. So we have tied it to smoking. We showed the relationship between exercise and smoking, showed the relationship between exercise and Alzheimer's, and thus show that that's the thing, that's the lurking variable, that's the confounding variable. Problem number 5. As part of its 25th year reunion celebration, the class of 1988 held a reception on campus. In an informal survey, the director of alumni development asked 50 of the attendees about their incomes. The director computed the mean income is $1,000 of the 50 attendees is $189,000. In a news release, the director announced the members of our class enjoyed resounding success. Last year's mean income was $1,889,952. What would a statistical advantage of using the median of the reported incomes rather than the mean be as the estimate of the typical income? So median is more robust and less skewed by outlier. Since income is likely to be skewed by outliers, median better represents the population, is more likely to represent the population. So the director felt that the members who have attended the reception may be different from the class as a whole. A more dedicated survey was planned to better estimate the income as well as other facts about the alumni. The staff developed 2 methods based on the available funds to carry out the survey. Send out an email to all of the people in the class and ask them to fill out an online form. Or 2, select a simple random sample of members of the class and contact the members directly by phone. Follow up if necessary. So in the first method, you're going to have more people respond. In the second method, you're going to have fewer people respond. Which of the 2 methods selected for estimating the average yearly income of the members is better? You want to compare the 2 methods and the effects of each method on estimate. So method number 1 is likely to lead to bias. You have, it's a volunteer sample. Those with high incomes are more likely to respond. Leading to the statistic overestimating the actual income. So we say why that's a problem and what direction you have the bias going. Method 2. This is a good estimate of the population. So method 2 is better. It's likely to be an unbiased estimator. All right. Problem number 6, approximately 3.5% of all children born in a certain region are from multiple births. Of the children born in the region who are from multiple births, 22% are left-handed. Of the people who are from single birth, 11% are left-handed. So here's what you have. So single birth, multiple births, single birth, so this is 3.5%. So this is 66.5%. Nope, 96. 96.5%. Boop. 96.5%. You can split it again. So left-handed, right-handed, left-handed, right-handed. Of the ones from multiple births, 22% are left-handed. 22%, which means this is 78%. And from single births, 11% are left-handed, 11%, 89%. What's the probability that a randomly selected child born in the region is left-handed? All right, so the left-handed child, we're gonna do. Actually, I'm gonna do Desmos. So. So we're going to do 0.965 times 0.11 plus 0.035 times 0.22. So 0.1139. So 0.1139. What is the probability that a randomly selected child born in the region is a child from multiple births, given the child is left-handed? So given that the child is left-handed, that's my denominator. what is the probability that the child is from multiple births? So we're going to put V 0.035 times 0.22. So 0.0077. So So 0.0676. A random sample of 20 children born in the region are selected. What's the probability that in the sample at least 3 children are left-handed? So this is binomial, with my n being 20 and my probability being 0.1139, and I'm going to find the probability that x is at least 3. And you want to know how to do this on the calculator. So it's going to be like menu 5B. And unfortunately, I can't do it because I don't have my calculator here. But I'll show you how to do it on Staplet. But you do want to know how to do this on the TI Inspire. So normal distribution, I have 20 people. The probability of any single one of them, is it 1139? I don't remember. That seems right. Yes. Plot the distribution. The probability that at least 3 successes. The probability of that is 0.4024. 4024. But again, know how to do this on the TI Inspire. So, but like this is the answer you should get. So you should look up how to do that and practice it. A shipping mall has 3 automated teller machines, ATMs. Because the machine receives very heavy use, they sometimes stop working and need to be repaired. Let a random variable x represent the number of ATMs that are working when the mall opens on a randomly selected day. The table shows the distribution. What's the probability that at least 1 ATM is working when the mall opens? So at least 1 happens here, here, and here. And actually the faster way to do that is 1 minus 0.15, which is 0.85. What's the expected value of the number of ATMs to be working when mall opens? All right, expected value. Once again, I'm going to use Desmos to find the expected value. So it's going to be 0 times 0.15 plus 1 times 0.21 plus 2 times 0.4 plus 3 times 0.24. So 1.77. So I expect 1.77 ATMs to be working on average. What's the probability that all 3 ATMs are working when the mall opens, given that at least 1 ATM is working? So we figured out that the probability of at least 1 ATM working is 0.85. And what's the probability that all 3 are working? So 0.24 over 0.85. 0.24 over 0.85. 0.28 to 2824. So 0.2824. Given that at least 1 ATM is working when mall opens, would you expect the value of the number of ATMs in the working, the value of the ATMs that are working to be less than, equal to, or greater than the expected value from B? So if at least one of them is working, I would expect the value to be more. Because we no longer have the possibility of none of them to be working. So basically, like, the idea is now we're just dealing with this, and these numbers have to add up to be 100. So just everything is going to be bigger. So once we remove the 0 from the calculation, everything else is going to go up in value. So yeah, that's that probability question.